good afternoon everybody. So, we are discussing stability of structure. So, this is a second class structure. So, we have introduced the concept of structural stability, okay, and we have discussed that why stability is important, okay, why analysis of stability is is important for both for design's perspective as well as to avoid kind of instability in structures, right, which is one form of failure, right. So, and we also briefly recapitulate the the contribution that were made by prominent scientists in this area, right, starting from the Euler buckling load in 17th century to modern concept of dynamic stability, namely the aerodynamic floater, and then follower force instability of a simple beam or column rather under follower forces, okay. And then we have started with the concept of stability. We have started with the simple system that we have learned in our school level physics, that how we define stability there is we were considering three situation where we were considering a ball that is resting on a convex concave bowl, right, and then you can see that this ball is under equilibrium because its weight is resisted by the reaction exerted by this ball surface, right, and then if you perturb this ball here, then because of its component of its weight, it will come back to its original configuration, and that is why it is stable configuration, right. Now, consider the situation where this ball is kept on a convex surface, and then if you perturb it a little bit, then it will diverge from its configuration, it will never reach back to its original configuration. So, this is unstable, right. And there was a third possibility where this ball is kept on a horizontal surface. So, wherever you place the ball, it will be there. So, even if you perturb it, okay, it will remain on that surface, right. So, this is called neutral equilibrium. So, the concept of stability were explained using these three simple example, qualitative example rather in our school level physics. So, we are trying to generalize this concept for our more advanced studies or treatment that we are going to give to structural stability, okay. So, the first lesson in a stability of structure is that you have to consider equilibrium, but in the perturbed configuration, right. And knowingly or unknowingly you might know these things, if you can briefly recall that when you were taught the stability of column, rather the buckling of column, then you have written down the beam bending equation in the perturbed configuration. Please recall that we know the beam bending equation, right. EI d4 w dx4 is equal to minus qx, right, or if you want to write in terms of bending moment, then EI d2 w dx2 is equal to minus mx, right. So, m is the bending moment, right. So, how this bending moment is coming there? So, we have considered a column, right, and then we have written the we have perturbed it. We have written down the equation. So, it was subjected to some force P axial compressive load, axial compression. So, you must have you must be recalling that this was perturbed, and then there was some deflection Wx, right, and that is what it is going to cause bending moment Mx, right. We are considering this m is x, this coordinate, right. So, if this is W, then P into W, right, and then we can m is nothing but minus EI d2 W dx2, right. So, there we got the column buckling, and that is where if you solve this difference. So, now you are getting an equation which is d2 W dx2 plus P by EI W is equal to 0, right? And that's what you solved to get the Euler critical rule, right? So why trying to emphasize, because I want to relate with your undergraduate, mechanics that you have learned. In stability, you have to write the equilibrium in deformed configuration. Okay, so so you have to perturb it. Okay, and then you have to see the equilibrium. Now, for column it was simple because it was a one dimensional system, but if you want to extend it for the 3D continua, you have to write down the equilibrium equation in terms of in deformed configuration. Then the equilibrium equations will be little different. That's where here I will briefly touch upon those issues. You can recall that in your solid mechanics course, right? If it is infinitely small deformation, then it was everything is expressed in Cauchy stress tensor, right? And that's where you have written that sigma ij comma j is equal to 0. That was equilibrium equation, right? In terms of Cauchy stress tensor. But then you are introduced with the other alternative stress tensor, like first Piola-Kirchhoff stress tensor, second Piola-Kirchhoff stress tensor. And if you can recall that in first and second Piola-Kirchhoff stress tensor, we have distinguished the deformed and undeformed configuration. So there if you consider second Piola-Kirchhoff stress tensor and first Piola-Kirchhoff stress tensor, then you can also will be able to write down the equilibrium equation in the deformed configuration in a continuous perspective. All these things will come later, okay? And you will see that we also briefly explain that finite deformation, when the deformation are not infinite small, okay, you have to have correct representation of the, or you have to establish equivalency of the deformation measures, okay, in order to correctly reproduce the strain energy functional, okay, or potential energy functional, okay. Those things we will discuss briefly. Now, what we have considered a example, small example to illustrate this equation, right? So, if you can recall that we were considering elastic system. So, in this example, we are considering elastic system. First, let us discuss the elastic stability. This course primarily deal with the stability of elastic structure, elastic stability. Okay, we will hardly discuss the inelastic stability and others. Okay, nevertheless, those are advanced treatment, and you can find in other courses. So, in elastic system, so we have considered that any elastic system will have some potential energy. So, we have developed, right, this is nothing but potential energy, and if you recall, potential energy for an elastic system can be expressed in terms of strain energy minus work done. So, U is nothing but strain energy, elastic strain energy, and you know how to calculate that, how to estimate that, and W is the work done, right, work done. So, then if you can recall in equilibrium, when we consider the static equilibrium, then we have obtain the if we consider the elastic system which have some degrees of freedom, okay. So, elastic system, so degrees of freedom we have defined as in terms of some vector theta, right. So, del pi del theta must be equal to 0. So, you get the sets of equation for the equation of equilibrium. So, that is the 0th order information or first order information that we learned, So, this is for establishing the equilibrium. You will see that what will be the equilibrium equation. That's what we have used in statics, even in dynamics to solve the system. Now, for stability, you have to consider higher order information. How? Please recall that we are perturbing the system, right? So, from the previous class, you can recall that we have done a Taylor series expansion. We have considered the expansion of potential energy functional phi, right? So, here it was theta, and then we have put some perturbation to theta. So, theta plus delta theta, right? So then if you can recall pi cos theta, right, plus del pi del theta, d theta, right, plus 1 factorial 2 del 2 pi, del theta theta d theta d theta here, or if you want to put it in that way, so so here these are when you can also express this is summation of pi is equal to 1 to number of degrees of freedom del pi del theta I or delta theta I, right, this one, and this one you can also write, there will be two summation over I and j. I am considering n degrees of freedom, so then del 2 pi del theta I theta j d theta I d theta j, right, or instead of d theta we can write del theta, right, delta theta, okay, instead of d theta here you write delta theta, right, delta theta, okay. So here you write delta theta I delta theta j, okay. So you can see that this is what this will give you, so here this you are going to get equilibrium equation, right, some k theta is equal to 0 or k theta is equal to, if there is some external load then there will be some load vector, okay. Whereas this higher order term, this higher order term will be another matrix of potential energy, okay. So this is second derivative of the potential energy term, right. So this matrix is Hessian, this is Hessian matrix, right, Hessian matrix of the potential energy, and what we have seen that when we are perturbing a system, so from theta we are going to delta theta, so then well this is being 0, right, so it does not really matter whether delta theta is positive or negative, okay, any perturbation it can be positive side, it does not really matter, right, since this is 0 this will vanish, but then so that means you have attained equilibrium, right. So now because of that perturbation, if the alternate configuration is is having higher strain energy, then the equilibrium that we are attaining will be stable, right. That means if this is greater than 0, because you see, because these are appearing in square, these are square, right, delta I delta j, so basically this will always be what, positive, right. So this term need to be positive, right, okay. So how will I ensure that? Well, if you make the determinant of the Hessian matrix positive and all its principal minors, okay, are positive, then that means this term is always positive. That means from theta to theta plus delta theta, if you go to an alternate configuration due to this perturbation, that will lead to a higher strain energy, okay, higher potential energy. That means our system will not go to that, will not attain that configuration, it will try to remain in this configuration. That means that equilibrium is stable. So you see how stability, so whether equilibrium is ensured by the gradient of the potential energy, when you want to ascertain the nature of equilibrium, that means whether it is stable equilibrium or unstable equilibrium or neutral equilibrium, we have to explore on higher order derivative of the potential energy, and that is where it is second order is Hessian matrix, okay. Now please note that you also have learned this Hessian concept in those of you who did optimization, right, because you must have done this step-based gradient method, right, numerical search technique to attain the maxima or minima, right. So which direction your search will be guided, that also depends on the sign of the Hessian matrix, right. So now, so you understand from here that how we define stability of equilibrium, okay. We have defined equilibrium by the gradient of a potential This defines equilibrium. That's what we have learned over all our mechanics course. Minimization of the potential energy is the equilibrium, right? Now for the stability of equilibrium, which is a higher order information, stability of equilibrium, which is a higher order information, you have to consider higher order derivative of theta I delta theta j. Okay, this determinant of this must be greater than 0 and all its principal minors, right? You know what is principal minor, because you just take diagonal term and then the subdeterminant must be greater than 0, right? So if it ensures, then it is stable equilibrium. If it is negative, that is unstable equilibrium. If determinant and principal minors are 0, then it is neutral equilibrium. Clear? So first we started, see, stability, not necessarily that we have to follow a energy approach to analyze stability, but this is most intuitive, and a first class of stability started with this energy concept, because this is most intuitive to us. Okay, and please note that it is easy to deal with the potential energy functional. Energy approach we always love. Why? And if you can recall that red book, energy approach in structural mechanics, that's a very celebrated book actually. Everybody, all these great mechanicians, they read that book. Okay, why? Because the energy approach is a very powerful approach, right? Okay, so we are going to illustrate this using a simple system that we have discussed in previous class. We just recapitulate whatever we have done in the previous class. So now, if you can recall that we were considering a 2 degree of freedom system, which is made of there was this rotational spring, and this is a rigid bar that is also connected with another middle. Okay, this is a rigid bar, right? So these are all rigid bar, and these are rotational spring. So rotational spring, that means they will exert moment on application of rotation, and it is subjected to some axial load P, okay, and we are asked to study the stability of this system. So the concept will be illustrated with respect to that simple toy problem. Okay, now why we have considered this? Well, this is not a real structure, but nevertheless it is a simple structure which has concentrated elasticity, because this is concentrated here, this is concentrated here, right? And I am assuming this is of length L by 2, this is of length L by 2, and all these two rotational springs are behaving, moment is C into theta. Theta is the relative rotation between the end, right? This is bending moment, and C is the rotational stiffness, right? So then we have written down the potential energy, and we have, so what if you can recall, I am not going to write down the equations, because I have done in previous class, but you have the expression for that, right? So I am writing potential energy is nothing but strain energy minus work done. I am assuming that initially that are straight, right? There is no imperfection, so potential energy U was basically, and I am perturbing it. Perturbing it means, when I am perturbing this, this is attaining a deformed configuration where this will it is rotating, so it will come here, and then with respect to this, there is going to come somewhere here, So I am defining here, this is angle is theta 1, and this angle from here it is, I am defining this angle is theta 2, and this P is coming here, right? So that is the way the springs are in action. So please note that I can use a different, so here was the spring was there, and then here the spring is there, and this rotation is happening with respect to this vertical axis, right, theta 1. So please note that on strain energy here, strain energy is nothing but the half m into theta 1, right? And m is nothing but c into theta 1. So half theta c theta 1 square, right? So half c theta 1 square, that was the strain energy in the first spring. What about second spring? Please note that in the second spring, it is the relative rotation that is important, right? So I have to expand it like this. So this angle. So this is rotation theta 1 with, from the vertical axis. This is from vertical is theta 2. So relative rotation here is nothing but theta 2 minus theta 1. Okay. So then the next expression is half theta c theta 2 minus theta 1 square, right? So this is the expression for the strain energy, elastic strain energy, and please note that this is concentrated elasticity. Okay. And then what is work done? Work done is done by this load P. Load P, why? This load P is coming to a distance, this distance vertically downward delta, and this delta is what? Delta is nothing. So I am writing P into the delta, and this delta that is nothing but vertical deflection of point of application of load P will be what? Is nothing but what? L. Initially these are all length L by 2, L by 2. This is length L by 2, this is also length L by 2, right? So initially there was this L minus L minus what? L by 2 cosine of theta 1 minus L by 2 cosine of theta 2, right? Because projection of this on this is L by 2 cos theta 1, projection L by 2 cos. So if sum these two, and so this much is basically the deformation, right? And then what we have used the expand. There is no, I mean, you do not require to simplify it using, just because it is appearing in terms of a polynomial, we also wanted to use some expansion of L by 2, okay, expansion of cosine theta trigonometric function in terms of polynomial, okay, and there is advantage to that I will explain you later. So this is L, if you can recall, this we have simplified, and that was L minus L by 2 cosine of theta 1 plus cosine of theta 2, and that was L minus L by 2 cosine of 1 minus theta 1 square by factorial 2 means 2. Higher terms I am neglecting, okay, but you may consider it. Later we will consider it. Theta 2 square by factorial 2. So this was, what was this after simplification? This was L by 2 theta 1 square plus theta 2 square, right? L by 4, right? Okay. So I am once again simplifying it. So half c theta 1 square plus half c theta 2 minus theta 1 square minus p L by 4. Please note that this is some approximation, because trigonometric function is approximated in terms of polynomial. It will be theta 1 square plus theta 2 square, right? Everything is in terms of a polynomial. Clear? Okay. So we express the potential energy functional. Why? Because it is a function of a function, right? In terms of polynomial. Now we will first find out the equilibrium. So we will use the zeroth order information, equilibrium. How will you ensure equilibrium? Well, del pi, this is 2 degree of freedom system. So theta 2 degree of freedom system, theta is basically theta 1 and theta 2, theta 1 and theta 2 are the degree of del till theta 1 0, and del pi del theta 2 is equal to 0. This, if you differentiate this pi with respect to theta 1 theta 2, so you will get the simplified equation. Equations I am writing. So this will give you, first one equation will be 2 c theta 1 minus c theta 2 minus PL by 2 theta 1 is equal to 0, and the next one c theta 2 minus c theta 1 minus PL by 2. You understand that? So here you see that this is giving we are obtaining to what? To simultaneous equation, but these are these are homogeneous system of equation, right. So, if you want to write in matrix form, if you combine them, then what you will get 2c minus PL by 2, c minus PL by 2, and this minus c, this is theta 1, theta 2 is equal to 0, 0. Now, say, so the equilibrium itself is giving rise to a what? To a homogeneous systems of equation, right? These are homogeneous systems of equation. Homogeneous system of equation, right? System of equation. Now you tell me, if it's homogeneous system of equation, then what? There can be a trivial solution where theta 1 is equal to 0, theta 2 is equal to 0. That means whatever be the system, if it is trivial, that's a trivial configuration, right? If theta 1 is equal to 0, theta 2 is equal to 0, then there is no other things, but vertical configuration. There is no perturbation, right? But if equilibrium has to be maintained in a perturbed configuration, right? Then you have to solve this. So how will you get a non-trivial solution? For non-trivial solution, what happens? For non-trivial solution of this system of equation, the determinant must be equal to 0, right? So 2c minus PL by 2 minus c and c minus PL by 2, that must be equal to 0. So please note that here it lead to a eigenvalue problem. So this is what? This is an eigenvalue problem, right? When I am writing the determinant is vanishing, that means this leads to eigenvalue problem. Eigenvalue problem. So what we see that stability analysis is for the given system, and the same thing you can recall now from your mechanics, column buckling formulation. There, see here it's a algebraic equation, that's what it's matrix form, but there it was in differential equation form. EI d2w dx2 plus pw is equal to 0. There it was also homogeneous equation, right? But that was differential equation. That is also eigenvalue problem. But that was, the solution was in terms of a trigonometric function, cosine and sine. So that was, we used to call it what? Trigonometric eigenvalue problem, whereas this is algebraic eigenvalue problem. You have seen similar kind of algebraic eigenvalue problem where, when you study structural dynamics. In structural dynamics, you free vibration problem you solve, right? That is nothing but that giving rise eigenvalue problem. Eigenvalues gives the natural frequency, and eigenvectors give the mode shape or vibration. Here, the eigenvalues will give you the values of the P, for which it will have a alternate configuration, whether it is stable, unstable or neutral, that we have to see. That means critical load you will get by solving this, and the eigenvectors will give you the buckling mode. We shouldn't call it buckling, but we can call it buckling because it is also a column with concentrated elasticity, right? A column will have a distributed elasticity, but it's concentrated elasticity. So this will also, by solving this eigenvalue problem, we will get the critical load and the critical buckling load and the respective buckling mode shape, eigenbuckling mode. Okay, let us solve this. So you find the characteristic polynomial 2c minus PL by 2, c minus PL by 2 minus c square is equal to 0, and if you simplify it, then you will get it. If you simplify it, then what you are going to get is, let me write it down. You will get an equation in the form of p square L square minus 6 PCL plus 4 c square is equal to 0, and this is a quadratic equation, so it will have two value, it will have two roots, right? and it is expected because it is a 2 degree of freedom system. So, by solving this you will get P is 2 value, okay. It is CL 3 plus minus root 5, or I will just denote is P critical 1 2. So, pre critical 1 and P critical 2. P critical 1, if you solve it, then you will see the value will be 0.38 C, 0.382, 0.382 C upon L, and here it is 2.618 C upon L. So, here you please see that. So, these two load, at these two load you can have an alternate equilibrium configuration, but that is in perturbed configuration, right. So, system can remain in equilibrium in a perturbed configuration, right, and these are that the value. So, this is critical load 1, this is critical load 2, clear. Okay. So, other than these two, we will also find out what Eigenbuckling mode, right. So, we will see that buckling mode. So, how will you find out buckling mode? You just, so you will see that stability problem, linearized stability problem always lead to a Eigenbuckling problem, okay. So, you know how to find out the buckling mode, right, you can find out the eigenvectors. So, eigenvector I am directly writing, okay, without finding it out. This eigenvector will be √5 minus 1 to 1, or if you simplify 0.6181, and here it is minus 1 minus √5 1 1, or it is minus 1.6181. So, these are the, so all of you know how to find out eigenvector, right. So, you basically consider the same system and you consider theta 1 to be 1, then you find out respective theta 2. So, eigenvectors means it is only in relative sense, right. You can always normalize it, by for a using its L2 norm basically to so that its a norm is 1, but here I didn't normalize, I just keep the top one as 1. So, so here you see that first this one, the eigenvector, I am going to write phi 1, I am going to write phi 2 as this one is 0.6181, and here it is minus 1.6181, okay. Now is that, so what are these represent? First one represent, you see that, so this was the this was the state configuration, right, this one, right, okay. So, first is the alternate configuration. So, Eigenbuckling mode represent the relative deformation of the 2 degree of freedom, okay, during when they attain this critical load, okay. So, at PCR1 first critical load, which is 0.382 C by L, it you see that 0.618 and 1, right. So, theta 1 theta 2. So, theta 1 means it is rotating like this is rotating like this, okay. So, it is going here, maybe it is going here, and this other things is going here, okay. So, this one is unity, and then this one is 0.618. You see that, but both are at the similar, both are in the same direction. You see that. So, both rotations are positive, right, either positive or negative, right. So, eigen modes gives you relative distribution of their deformations, not absolute, right. This is mode, say mode 1, buckling mode 1, and then what about buckling mode 2? Buckling mode 2, here you see that the first one, the theta 1 is negative, right? So what will happen here? See, negative means if I put it like this, something like this, then the other one will come as, it will be something like this. So you see that this one, it's a minus 1.618, and then from here it is coming here. So then this is 1. This unit. So this is clockwise and this is anti-clockwise. Do you see? So if this one is moving this direction, the other one is moving in this direction. So the buckling mode 2, there you see that they are having opposite sign, right? So do you find the similarity between with the structural dynamics? There the mode shape represent the Hessian modes, right? Free vibration, right? Here they are buckling mode. Clear? Okay. Now here you must understand one thing, that what we have learned, that eigenvector can serve as a legitimate basis. So we can have a basis transformation, right? We have considered that theta 1, theta 2, theta 1, theta 2, those are the value, right? We can have, and theta 1, theta 2 are coupled. We can consider another basis y1, y2, right? Or theta 1 bar theta 2 by putting these eigenvectors, where this is 0.618, this is 1, and this is minus 1.6181. So this is, I am calling it this, matrix containing the eigenvectors. So this is called modal matrix, right? This is called modal matrix. Modal matrix. The way we have used this eigenvector to get the uncoupled equation from the coupled, here also you please note that transformation, okay? Later we will talk about it. So phi 1, phi 2, theta 1, theta 2 can be expressed, so this is kind of linear transformation, right? I mean, some kind of similarity transformation. You can use this, coordinate transformation, okay? Basis, transformation of basis, okay? We will come there later, but please recall that. Why? Because mode shapes gives us a sets of legitimate basis that can be used for coordinate transformation. Clear? Please note that. We will come there later and I will tell you something interesting in stability context, okay? Clear. But here, now, we have considered the first derivative. So we have established our alternate equilibrium configuration, right? Now, we will see the nature of stability, okay? So, the stability, stability. So, for stability, what we will have to do? Second order derivative, right? So, we have to find out del 2 pi, del theta 1, we have to find out del 2 pi, del theta 2, we have to find out del 2 pi, del theta 1, del theta 2, we have to find out del 2 pi, del theta 2, del theta 1. So here we can clearly see, so del 2 pi del theta 2 is nothing but 2c minus PL by 2. If you can recall, we have find out the first derivative, right? We have find out the first derivative, so you just differentiate it once again. So del 2 pi del theta 1 2 is nothing but 2c minus PL by 2. Then del 2 pi del theta 2. Del 2 pi del theta 2 is nothing but c minus PL by 2. Another thing, did you see that the critical load PCR is a function of what? The alternate configuration. In alternate configuration, the whatever load is a function of what? C and L. That means it is the length, geometric parameter as well as the stiffness, right? Why it is so? So similar to buckling load, pi square E by L square. EI is stiffness, L is geometric parameter, right? Okay, good. So then del 2 pi del theta 1 theta 2 is nothing but minus C. Okay. So please write the Hessian matrix of the potential energy function. So, Hessian matrix of the potential energy functional being 2C minus PL by 2, right, and this is minus C, this is minus C, and this is C minus PL by 2. Now, we have to see that, well, I mean, so we have to find out the determinant, right. So, determinant need to be positive for the stability, right. Let us find out determinant. So, determinant, if you find out, what you will get, 2C minus PL by 2, C minus PL by 2 minus C square. You will see that this expression is same as the expression for the whatever you are getting for the quadratic equation, minus 6 PCL plus P square L square. Okay, that means, may I write it, P minus PCR 1, and may I factorize it like this, PCR 2? Can I do it? This is not square, please note that this refers to the this 1 to superscript refer to the first and second critical load. May I do it like that? Clear? Because it is the same polynomial, same second quadratic polynomial, that, so you can factorize like that. So, that is the Hessian. Now, other than Hessian, what else? What else? Hessian need to be positive for stability, right? Keep it. So, this must be greater than 0 for stability. Okay. So, for stability, so for stable equilibrium, right? For stable equilibrium, P minus P CR1, P minus P CR2 must be greater than 0. That is the first condition, right? Clear? What about other condition? Principal minor. What are the principal minor? Principal minor is nothing but the diagonal term, right? So, this diagonal of this diagonal term. So, principal minor now, principal minors, right? Minors. What are the principal of this one, right? 2C minus PL by 2 must be greater than 0, right? What does it implies? This implies that, well, 2C greater than PL by 2, or P must be less than 4C by L, right? And the other one is what? Other one is C minus PL by 2, right? Must be greater than 0. So, here it is C greater than PL by 2, or P less than 2C by L. Understand that? Here you must recall the value of PCR and PCR2. You must keep it with you. So, what was its value? One was what? What was its value? Yes, so it was, I think, 0.382, right? 0.382 C by L, C upon L, and then it was 2.6180 C upon L, right? Okay, now, see, well, so all these three conditions need to be satisfied for stability, right? Now, you tell me, how can it be greater than 0? If this greater than this one, this also greater than this one, right? So, P must be greater than CR1, and P must be greater than PCR2, right? This is one. Or P must be greater than PCR1, and P must be also greater than PCR2. But then if it is greater than PCR1, it automatically greater than PCR, you see? Or there can be another thing, P less than PCR1 and P less than PCR2, right? There is another, because both, if the both are negative, then negative it will be positive, multiply, right? So, which one is more? But then if see, P must be less than 2C by L. So, which condition will satisfy? See, if PCR is this, see, this must be less than 2C by L, right? If it is 2C less than 2C by L, it is automatically less than 4C by L. So, it must be less than 2C by L, and also it need to be less than this value for it is getting satisfied, right? Because if it is less than PCR1, it is automatically less than this, you see, clear? So, then it is only stable, otherwise it is unstable, right? So, I will just draw a diagram here now that I am removing this. So, I will just draw this. This is theta 1 or theta 2 both. Either you can go this and this, okay. So, I am drawing P. So, there is 2 PC, this is one PCR1, PCR2, right? PCR1 and here it is PCR2, right? So, if P less than PCR1, if P less than PCR1, only this one, then only it is stable. If it is here, it is unstable, and here also it is unstable, right? Do you understand? All of you understand? Because then only if it is less than PCR1, this is satisfied, this is automatically satisfied, and this is also satisfied. If P is less than PCR1, this is negative, it is also negative, positive. So, and then, so if P is less than PCR1, then only it is stable, other all it is unstable. And when P is equal to PCR1, what is happening? Double derivative, this is being 0. 0 means what? Neutral. That means at critical load it will be all neutral equilibrium, right? It is neutral. And you also recall that when it buckle basically, just when it is just on the verge of buckling, it is what kind of equilibrium it is? Neutral, because you can perturb it and you can keep it at any configuration you want, right? That is what we can see. So, what we can see that the system will remain stable, but then it will bifurcate into a state at the first critical load. Why bifurcate? Because from here it is theta 1 theta 2 0, here theta 1 theta 2 0, but then it is being bifurcating because if you want to attain an equilibrium other than theta 1 theta 2 0, right, then what will happen? Then it will, so what is happening if the load P is less than PCR1, then whatever configuration you put it, you perturb it, right? First of all, then it will be in stable equilibrium configuration, right? It is stable, right? Equilibrium is only possible at P is equal to PCR1, right? But then this equilibrium configuration is neutral, right? And what is happening? Then when you are perturbing it, then then either it is going to this side or it is going to this side. You understand? So, it is basically breaking the symmetry, okay. I will come there, I will come there later when you incorporate, because symmetry breaking is a more generalized concept that is used in physics. Your physics friend and others, they use this big. So, the system is bifurcating. This point is what? This is a bifurcation. System is bifurcating, right, into an alternate state. Look, from here to here, theta 1, theta 2, 0, but then system is bifurcating. Of course, for theta 1, theta 2 has to maintain those kind of modes of, relative ratio between the two, but then system is bifurcating into a state where it is losing its symmetry. Why it is losing its symmetry? Because look, when theta 1, theta 2, 0, this is fine, right, it is symmetric, but then when it is, losing its stability, you see, when it is in alternate configuration theta 1 theta 2, right, then the system will remain there, so it will not come, it goes slightly beyond that, then it will diverge towards this, it will not come, you see. So it will not distinguish between see earlier it was not distinguishing whether it is, why you used to call that breaking of symmetry, because earlier it was symmetric, keep it here, if it is, as long as p less than this one, it will come to this position, right, is symmetric. Any of the configurations, it can remain and it will come back to its, because it is a stable, right, equilibrium, right. But as soon as it is exceeded, then the system is bifurcating into one direction. You see, consider the buckling, what is happening. So same thing is buckling, right. So the column is, column is there. So if the load P is less than P critical, if it is the axial load is less than critical load, then you just perturb it and leave it. Then whether you deflect it positive, negative, it will come to original configuration. So it is basically with respect to any perturbation, it will retain its symmetry, right. But as soon as it critical load is exceeded, then what is happening? Then the system is bifurcating. Bifurcating why? Because as soon as you are exceeding this, see, when it is at critical, then it is in neutral equilibrium, but slightly above this, then it is unstable. Then it will diverge to in one direction. That means it is no more coming back to original configuration, it will diverge in one direction. Either if you are perturbing in positive direction, it will go on to be positive, it is going to be negative directions, right. So it distinguishes, so that means the symmetry is broken. This phenomena is called symmetry breaking. And why this is called bifurcation. Why it is called bifurcation? Because a stable configuration, is bifurcating in alternate configuration. This one is bifurcating. Clear? Okay, now, so you understand the stability, all these things. Now, I will do one simple stuff. I will do one stuff that you can all recall that we have this eigenvector and then we have this modal matrix. I have written the modal matrix was written as, I have written, either you can write in terms of this minus 5 minus 1, 2 minus 1 minus root 5 by 2, or you can write it, in terms of these values when you are normalizing 0.618, 1 minus 1.6181, right. So potential energy pi was what? Potential energy pi was, if you can recall the expression, half c what? Half c theta 1 square plus half c theta 2 minus theta 1 square, right, and then minus p l by 4, right, p l by 4, theta 1 square plus theta 2 square, right, that was the expression, right. Now, what I am saying that if this is phi, you can convert theta 1 theta 2 to be whatever these values are, 6181 minus 1.6181, and here you write y1 y2, or you can write theta 1. So from here, and then, so then theta 1 become 0.618 y1 minus 1.618 y2, and theta 2, it is a linear transformation, right, y1 plus y2, then you substitute back, and then you substitute here in the potential energy expression, substitute, substitute. Then if you substitute, what you are going to get pi as, you will see, you will get, I am not writing the coefficients, that you do yourself, b1 y1 square plus b2 y2 square. So here look, here what is happening, look, this is square, this is square, this is square, this is theta 2 square plus theta 1 square, but there was one theta 2 term, cross term, that means they are coupled. In potential energy function, there are coupling term between these theta 1 and theta 2. But if we do this similarity transformation using the mode shape basis, using the eigenvector as the legitimate basis, then your potential energy function become a function of this independent coordinate y1, y2, and there is no coupling term. No coupling term, you see that, no coupling term, no coupling term. That is what you also have done. Why did you do that? When you in dynamics course, when you did eigenvector and you made the transformation, and that's your stiffness matrix was become uncoupled, right? You pre-multiply and post-multiply with the eigenvector modal matrix, right? Here, because that was generalized eigenvalue problem, here it was just eigenvalue problem, normal eigenvalue problem. So, what is happening? B1, B2 are always positive. Well, may not be positive. There will be, for this system, B1, B2 will be always constant, right? It's a linear system. So, what we are trying to tell you is that, you see, this quadratic form of this potential energy function is very, very important in deciding the nature of stability. If all the terms are square or quartic, then they are always positive. So, square positive. Now, only so then you do not require to find out anything else. Just see the potential energy function, and if B1 and B2 are positive, then it is stable. Clear? So, by using this kind of transformation of coordinate, you can simplify the diagonal, you can simplify the detection of the stability. Where this B1 and B2, you see where B1 is positive or B2 is positive, both are positive, it is stable, right? Because there is no coupling term theta 1, theta 2, you see, and it will have a more important consequences later. I will come there later, but here I will show you something. What is happening when I am drawing the this configuration, right? This one is P, you see here. So, these are the important point, right? So, here when P less than PCR, this regime, stable regime, P less than PCR1, this regime, the potential energy functional will, so here it is, I will now, define, potential energy functional I am going to, plot, okay. This is theta 1, this is theta 2, theta 1, theta 2, okay. And this is y1 and this is y2. So, respective to this, I will just, respective to this, I am going to put like this, okay. So, here the potential energy function, here, if you, so, if you plot it, here you will see, the potential energy functional will look like, so, it will look like a ellipsoidal paraboloid, okay, elliptical paraboloid here, okay. So, it is a like this kind of surface, elliptical paraboloid, okay. Here it is elliptical paraboloid. So, potential energy function is always concave. Here in one direction it is ellipse, another in direction it is parabol. It's a solid object. Do you see that? So, it looks like a bowl, okay. So, why it is when P less than PCR? That means any ball you put it, so it's a concave surface of the potential energy, and if it is a concave surface of the potential energy, then it implies stable configuration, right? Here what is happening when P is equal to PCR? P is equal to PCR, what is happening is that it is being, it will become, this kind of cylindrical, you know, one thing is cylindrical. Cylindrical means what? In one coordinate it is concave, but other coordinate it is neutral. Then when you are reaching here, then it is being, you know, like this, you know, but you know, this configuration is also being like this. So it is cylindrical, but the surface is also convex. Okay, and in between here, between this and this, it will be, I mean, you know, it will be something like this, you know, unstable. So it will be something like this here, something like this here, you know, here, and this will also be, you know, so it is not, this is also convex, this is also convex. You see that? And then when you come to this, here both side will be, you know, it is ellipsoid paraboloid, but here what is happening is that here it will be, it is convex elliptical paraboloid, convex elliptical paraboloid. Here it is concave elliptical paraboloid. Okay, here it is being, you know, cylindrical, you know, you know, cylindrical, you know, ellipsoid or cylindrical paraboloid, whatever. Okay, do you understand why this form is coming? If the potential energy functional being convex, you know, then you see that it's Hessian, it's Hessian being positive all the time. Okay, that's why it, you know, because of change of slope, you know, change of slope is positive and change of slope is also positive, you see. So this convex, this is the potential energy function. Here it is completely unstable. So this is convex, this is completely concave. In between, along one direction, it being cylindrical. Cylindrical means what? If it is flat cylinder, then it will remain what? It will remain what? Neutral equilibrium. That's what is happening PCR1 and PCR2. Because PCR1 and PCR2, your Hessian is being 0, your Hessian is vanishing. How can Hessian, if Hessian is vanishing, that means the equilibrium is neutral. That means here you see that at this point and this point, in this point, here this surface need to be, you know, one surface need to be cylindrical, then only it will be neutral equilibrium. Clear? So this and this, you know, see here it will be like this and here it will be something like this. Here it is something, see, if this one is along, this cylindrical axis aligned along y2, then this cylindrical axis will be aligning along y1, theta 1, okay. So here I am actually unable, one second, let me, you know, try to understand it nicely, okay. So you see how here I am drawing it. Do you understand? See, at P is equal to PCR1, what is happening? This. So along other it is neutral equilibrium, okay. Similarly, the other, you know, here it is aligned along theta 2, okay. I am not very particular about theta 1, theta 2, that you can decide which one, but and in between, that means between this and this, it will be this will not be perfectly cylinder. Cylinder will have a concave surface. Okay. So in between this, what will have? It will have this and this, and but then it will have a concave surface. Clear? All of you understood what I am trying to. So it's the shape of the potential energy functional that matters a lot in determining the stability. Okay. Here it is fully concave, here it is cylindrical. So along one axis it is basically in neutral equilibrium because it's Hessian being 0 and things. Okay. Now what I am trying to tell you is, if it is a equation of parabola and whatever, right? Because it is decoupled from here, you can see that what kind of equation it is. Okay, you can from your coordinate geometry you can recall the generalized equation of this conical sections, right? And then special equations, right? Y square is equal to 4x for parabola if it is in the its axis is along some either x is equal to 0, y is equal to 0. Otherwise, generalized parabola will all have this coupling term, right? Isn't it? So it is x square plus y square plus 2gx plus 2fy plus some 2fxy plus c is equal to 0. That's the generalized conic section. But if it is uncoupled the way by coordinate transformation we did, then for ellipse it is x square x square by x1 square by square plus x2 square by v square is equal to 1. If it is aligned major axis minor axis is along the main axis, right? So this is uncoupled form, which is much easier to deal with and understand that what kind of shape is this. So when I am talking about this, it's an elliptical paraboloid. If you simplify it, you will get this kind of form. Okay. So you understand the evolution of the potential energy surface and how it is affecting stability. Clear? Okay. So now what I will do, at least for this problem, I will put the effect of imperfection, right? Effect of imperfection. So imperfections means, we will consider geometric imperfection. That means earlier we assume this to be a perfect system, but here what we will assume that initially this bar had some kind of little crooked kind of things. You see that? So it was already having some imperfection of alpha 1. It was already having some imperfection in terms of alpha 2. Alpha 1, alpha 2 are initial imperfections. That means initial rotation. So instead of being perfectly straight, they are already having little inclination. So those are geometric imperfections. Imperfections alpha 1 and alpha 2 are the initial inclination. Initial inclination of the rigid bar, right? Of the rigid bar. If it is so, then how do we approach the problem? Potential energy function, how it will look like? Y strain energy minus work done. Strain energy will be half c theta 1 is fine, but earlier it was having alpha 1 imperfection. So the relative rotation is theta 1 minus alpha 1 square plus half c. Here theta 2 is also having imperfection, so theta 2 minus alpha 2 minus theta 1 minus alpha 1 square, and then the work done is PL by 4. Here you can understand that here it will be cosine of alpha 1 minus cosine of theta 1 plus cosine of alpha 2 minus cosine of theta 2. You understand why it is so, right? You understand why it is so, because of the initial alpha 1 inclination, it will have already L cos theta alpha 1, right? And then it is further being L cos theta 1. So L cos theta 1 minus L cos alpha 1 minus L cos theta 1 will be the actual deformation. That's what it is coming here, right? So if you repeat the same exercise and expand this cosine function in terms of their series expansion and do the whole exercise. And if you do the whole exercise, I am I will write down the final expression. Okay. So please have this potential energy function, right? So then I will just write down. So you will see that what you will get pi is half c theta 1 minus alpha 1 square plus half c theta 2 minus theta 1 minus alpha 2 plus alpha 1 square minus PL by 4 theta 1 square plus theta 2 square minus alpha 1 square minus alpha 2 square, right? And then you will see that, see, things will not, of course imperfection will have some influence, but I will just write down the equilibrium equation, So del pi del theta 1 is equal to 0 and del pi del theta 2 is equal to 0. This will give the system of equation. You will see that you will get this kind of things, 2 minus PL by C, this is, I mean, another form we are writing, 1 minus PL by C, this theta 1 theta 2 is 2 alpha 1 minus alpha 2 minus alpha 1, okay. So you see, unlike the eigenvalue problem, incorporation of imperfections is changing the the problem. It is no more resulting into eigenvalue problem. It is rather a static finding out the static equilibrium configuration, right? Because it's a non-homogeneous system of equations. So the way you solve for the static equilibrium, right, you can find out theta 1 theta 2 for given alpha 1 alpha 2. It is no more a eigenvalue problem. So incorporation of imperfections, you are basically breaking the type of the problem. And then you will see the, for the Hessian, del 2 pi del 0 1 2 is 2 minus PL by C, del 2 pi del theta 2, you will see the nature of equilibrium will not change. You will see that I am explaining to you. Del 2 pi del theta 1 theta 2 is minus 1 whatever, So here Hessian remain identical. So you see that here, so Hessian remains identical. So it will imperfection is not affecting the stability, but it is not always so. Please note that, just because it's a simple toy problem, so it will not, for this problem it is not, so it does not affect stability, affect the nature of stability, the nature of stability. Because these are constant terms, so second derivative, so here I am going to draw the same diagram, right, with imperfections. So stability diagram, I am going to draw the stability diagram. Stability diagram I am going to draw, here I am drawing theta 1 or theta 2, and here I am going to put phi, and then here it is PCR1, PCR2. These are for perfect structure when the bifurcation is occurring, that is characterized by the eigenvalue problem mathematically. But here what is happening, you will see. Please note that. These are the bifurcation point. Here you see this. This is only stable. This is unstable. Unstable. But now, what is happening? See, these are the imperfections. These are increasing alpha 1, alpha 2 value, alpha 1, alpha, increasing alpha 1, alpha 1, alpha 2. Increasing, okay? Increasing alpha 1, alpha 2. This is for different increasing alpha 1, alpha 2. Huh? What is happening is that basically, see, so there is no bifurcation because see all these in imperfect system, these are called equilibrium path because the first derivative when we are making it 0 we are getting the equilibrium path. Equilibrium paths are asymptotically approaching the bifurcation load. See that there is no bifurcation because a single part is not bifurcating into two. So, incorporation of imperfections in this is eliminating the bifurcation. But the equilibrium paths, these are called equilibrium path. Why? Because this path basically P, this is nothing but P, right? This is the relationship which satisfy the equilibrium. So, P in terms of theta 1, theta 2, you can obtain from here because that's where the equilibrium is satisfied. That's what I am calling them as equilibrium path. You said, but only these equilibrium paths are stable, all other equilibrium paths are unstable. So, stable equilibrium paths are given by solid line, whether these are unstable equilibrium path, unstable. And then all stable and unstable equilibrium paths are asymptotically approaching the perfect system. That's what is the generalized characteristics of any system. So, an imperfect system, imperfect system, the equilibrium path will asymptotically approaches to the perfect system. Because you know what is asymptote, right? You have find out asymptote pedal format in differential calculus, right? So, this is the stability diagram here for this 2-degree of freedom system, elastic system. So, you must recall that what we have discussed, we have solved a simple example and by using energy approach, we have seen how to find out stability, what is the nature of stability, how we can write down the functional expression for the potential energy, how we can do a coordinate transformation to make the coupled terms uncoupled and that will facilitate finding out stability and how to find out whether it is stable equilibrium configuration or unstable equilibrium configuration and then the influence of uncertainty, influence of imperfections. Clear? Thank you very much for today's class.